Welcome to the course Microelectromechanical System. Today's topic of discussion is microsensors. Let's discuss what's a sensor, then what makes a microsensor, what are the parameters that needs to be included to make it a smart sensor, what makes an intelligent sensor, and the type of sensors. A sensor is a device or a subsystem to detect events or changes in its environment and sends the information to an electronic device, probably a processor. With advancements in micromachining, the uses of sensors have expanded beyond the traditional system. Making the sensor smaller often improves its performance and may introduce many other advantages. So, you can say a microsensor is a sensor of size micrometer to millimeter that reaches a significantly higher speed and sensitivity compared to macroscopic apertures. A smart sensor unit should include automatic calibration, interference signal reduction, parasitic effect compensation, offset correction. It should be self-diagnostic and self-repair. If all these parameters like automatic calibration, interference signal reduction, parasitic effect compensation, offset correction, and if it is self-diagnostic and self-repairable, then you call such a system to be a smart sensor. When all these parts or all the processing functions integrated or on the same silicon substrate, then it makes it an intelligent sensor. Coming to the types of sensors, there are 6 types of sensors: acoustic wave sensor, biomedical sensor, chemical sensor, optical sensor, pressure sensor, and thermal sensors. Let's move our discussion to acoustic wave sensor. So, acoustic wave sensor will discuss about the introduction of acoustic wave sensors, history of acoustic wave sensors, the construction, working principle, and applications of acoustic wave sensors. When we move about the introduction, acoustic wave sensors are basically sensors which are used to sense mechanical and acoustic waves. Acoustic wave sensors or devices uses piezoelectric effect and inverse piezoelectric effect. In doing so, or for doing so, you use a piezoelectric material to generate an acoustic wave. So piezoelectric acoustic wave sensors works on the principle of both piezoelectric effect and inverse piezoelectric effect. When speaking about piezoelectric effect, refers to production of electrical signal changed by the imposition of mechanical signal. That is, when a mechanical stress is being applied, the mechanical stress is being converted into electrical energy. And this phenomena is reciprocal. That is, on application of electric field, if it is converting it into a mechanical deformation, then we call it to be an inverse piezoelectric effect. The piezoelectric substrate materials that are needed in sensing acoustic wave are quartz crystal in its crystallized form, lithium tantalate, and lithium nivolate. And lithium nivolate is less used compared to quartz crystal and lithium tantalate. An interesting property of quartz crystal is that it is possible to select the temperature dependence of the material by just cut edge angle and the wave propagation direction. By choosing the cut angle and the wave propagation angle, we can select the temperature dependence of the material. The advantage of using a acoustic wave is the slow speed of propagation, that is 5 orders of slower magnitude. For same frequency, the wavelength is 1 lakh times shorter than electromagnetic shortwave. This allows the fabrication, that is, the slowing down of magnitude, the slow speed of propagation of acoustic wave by 1 lakh times allows the fabrication of very small sensors with frequencies in gigahertz and with very fast response. Speaking about the history of acoustic wave sensors, in 1885, John William Studd first proposed the existence of saw acoustic wave. In 1950, first acoustic wave transducers were designed. In 1920, acoustic oscillators were developed. In 1960, it was suggested that acoustic waves were useful in electronic industries, and 1965 interdigitated transducers, IDTs, that is interdigitated transducers, were developed. Moving to the construction of the piezoelectric or acoustic wave sensor, the basic surface acoustic wave sensor device would consist of a piezoelectric substrate, right, an input IDT and an output IDT. On the one input IDT on one side of the surface and output IDT on the other side of the substrate. The space between the two IDTs is called the delay line. The space is called the delay line. It is so called because the signal or mechanical waves at this point moves much slower than the electromagnetic form, causing appreciable delay. Moving to the working principle of an acoustic wave sensor, most modern surface acoustic wave sensors use IDTs to convert an electrical signal into an acoustic wave when sinusoidal electrical input is supplied. It creates alternative polarities between the electrodes of the IDT, which creates alternative regions of expansion and compression of the piezoelectric material. In the next cycle, the negatively charged electrodes becomes positive and positively charged electrodes would become negative, leading to expansion of compressed parts and compression of expanded parts. The video would show the working of the acoustic wave sensor. You have an input IDT here and an output IDT. The input IDT, when supplied with an electrical signal, would convert it into deformations. That is, the positive charge and negative charge. Positive polarity would expand the piezoelectric substrate and the negative charge would compress the piezoelectric material. Thus, thus acoustic wave is generated. The generated acoustic wave thus moves through the expansion and compression and reaches the output IDT. The output IDT converts, right, the mechanical deformation into electrical signal. This is the principle or working principle of acoustic wave sensor. Speaking about the applications of acoustic wave sensor, acoustic wave sensors can be used as band pass filter, resonators, delay line, temperature sensors and pressure sensors. Speaking about how a acoustic wave sensor can be used as a band pass filter. Out of all the ranges of frequencies applied to the input IDT, only a small band of frequency appears at the output IDT with one center frequency which resonates with saw device frequencies. Hence, saw device can be used as a band pass filter. Speaking about the application of acoustic wave sensor as a resonator on increasing the number of electrode pairs in the IDTs. That is, in the IDTs, if the number of electrodes are being increased, the bandwidth becomes very small. This implies that SAW device can be used as resonators. Speaking about the application in as a delay line, velocity of electromagnetic wave is of the order 10 to the power 8 micron per second, milli per second. So while the velocity of acoustic wave is of the order 10 to the power millions per second. As the acoustic wave propagation over the surface of elastic medium, the velocity of EM waves becomes 10 times smaller, implying SAW devices can be used in delay line. That is, the velocity with which the electromagnetic waves move, that is 10 to the power 8 meters per second, is slowed down to 10 to the power 3 meters per second. Right? So there is a reduction of 10 to the power 6 times smaller. So thus you can say that surface acoustic wave devices can be used in delay lines or as delay lines. It can also be used as temperature sensors, right? If there are some changes in the ambient temperature, the velocity of acoustic wave changes. Because of the temperature coefficient of the material, in turn changes the output center frequency. Hence, SAW devices can be used as temperature sensors and pressure sensor. When applying pressure to the device, there is mechanical deformation which is converted into electrical signal, thus functioning as pressure sensor. Apart from these applications, with a minute change in the delay line, you can make it function as chemical sensors, biosensors, UV detectors, and further. One such example is shown here, acting as a chemical sensor. In the delay line, if you add an analyte and if the biomolecular substance is added onto the delay light, and when the analyte comes in contact with the biomolecular substance, there would be a chemical reaction taking place, saying you what is the amount of analyte present, what is the amount of substance present in the analyte. Thus, by coating the delay line by a biomolecular substance, you can make it function as a chemical sensor. Second one is this diagram shows you how it can be used as a biosensor. When we are discussing biosensors, we will discuss about this diagram in detail. This particular diagram shows you the This video speaks about generating a surface acoustic wave. We just deposit metal on piezoelectric substrate and apply voltage. This process is reversed. The incoming wave will be picked up by the metal and create a measurable voltage seen at the bulb. The energy caused by the bulb, energy carried by the bulb, will undergo a change. Say if it encounters a gas in its path, different gases will have different effect. We can add some liquid in the path of the SAW. We can see that this reduces the energy of the wave at the receiver. This means that the energy is transformed on the water molecules. A combination of energy and titanium nanoparticles can be used to split water into hydrogen and oxygen. Hydrogen generation is increased exponentially, which can be viewed in this video. Hope you understood the working principle of acoustic wave sensors. Thank you.